Hi, everybody. Welcome to our 7th chapter on climate. And this chapter is a very important one, and we're going to be covering a lot of ground in it because climate is a very important concept and a very complex concept. And so our list of learning outcomes for this chapter is pretty extensive. We are going to define both climate and weather and explain how the two are related. We will familiarize ourselves with the Celsius temperature scale as we do this. We will discuss the role and mechanisms of the major controls on Earth's climate, which include insolation, albedo, and the greenhouse effect. We will also identify and describe the mechanisms of major internal and external changes to the climate, which will include solar output variation, volcanoes, biological processes, changes in glacial coverage, and meteorite impacts. We'll look at the processes that can lead to a climatic state that is known as a snowball Earth and contrast the factors that influence this period in the Earth's history with other factors, such as the ones operating during the Cretaceous period. We'll look at the major ways that the carbon dioxide component of our atmosphere is added to and also removed from the atmosphere, and describe how carbon dioxide and greenhouse gases can be kept in balance. We'll describe the changing climate of the Quaternary, which is the current period of the geological timescale that we're in right now. And in doing so, we'll look at how processes called Milankovitch cycles explain the variations seen in climate over the Quaternary period. We will explain how the glacier and climate systems are linked through albedo feedbacks. We'll describe how sediment and ice cores provide information about past climates. We'll look at how stable isotope fractionation is used to predict the impact of changing climate. We will assess long-term global temperature records and place recent climate change into the context of historical temperature observations. And we're almost done, I promise. We'll explain how changes in the sun's energy output have impacted the past 1,300 years of global temperatures. We'll look at the ways that humans have influenced the Earth's albedo, as well as explain the initial and long-term effects of volcanic activity and why they are different. We'll explain the enhanced greenhouse effect, discuss how recent observations of changes within regional ecosystems are related to global climate change, and explain the relationship between fossil fuel usage and CO2 emissions. Yes, I know that sounds like a lot, but we will walk through it slowly and we will break it down into simple terms so that hopefully we understand it all. Before we get into the real meat of this chapter, though, we need to clarify two foundational ideas, one of which is the distinction between Celsius and Fahrenheit. So you probably know that these are both scales for measuring temperature, which is an important aspect of climate. And if you're born and raised in the US, the one that is intuitively known to you is probably Fahrenheit. If you were born and raised almost anywhere else, the one that is intuitive to you is probably Celsius. The US is one of only 5 countries that uses Fahrenheit as the official temperature scale, and the others are small countries like Belize and the Bahamas, and they're so small that you can barely even see them on this map on the screen. But because Celsius is much more common of a scale for measuring temperature in the context of the world, it's also the scale that's used in science. So we have to familiarize ourselves with the Celsius temperature scale a bit before we get started. So let's take a look at some of the temperatures that you might be familiar with in the Fahrenheit scale and compare them to the Celsius scale. So in Fahrenheit, water freezes at 32 degrees, which is the same as 0 degrees in Celsius. A comfortable room temperature in Fahrenheit might be around 68 degrees, which is the equivalent of 20 degrees in the Celsius scale. In Fahrenheit, the human body is 98.6 degrees, and in Celsius, it's 37 degrees. A hot summer day in Arizona, southern Arizona, might reach 110 degrees Fahrenheit, which is 43.3 degrees Celsius. And then water boils at 212 degrees Fahrenheit, which is 100 degrees Celsius. So one of the convenient things about Celsius is that the freezing and boiling are sort of anchored at 0 and 100, respectively. So those are easy to remember. And also another thing to note is that when water goes from freezing to boiling, as measured in the Fahrenheit scale, it goes from 32 degrees up to 212 degrees, which is a difference of 180 degrees. But when water goes from freezing to boiling in the Celsius scale, it jumps from 0 degrees to 100 degrees, which is, of course, a difference of 100 degrees. So, to cover the same amount of ground from freezing to boiling, Fahrenheit does it in 180 degrees, while Celsius does it in only 100 degrees. So, this tells you that the interval of each degree in Celsius and Fahrenheit is not the same. 1 degree Celsius is actually measuring a bigger change in temperature than 1 degree Fahrenheit. In fact, 1 degree Celsius is almost about twice as large as a degree in Fahrenheit. So keep that in mind when we're talking about temperature changes in Celsius. These are bigger jumps than would be reflected in our understanding of Fahrenheit. And of course, there is a standard equation that's used to convert between Fahrenheit and Celsius and vice versa. To get from Fahrenheit to Celsius, you take the number of degrees in Fahrenheit and you subtract 32, and then you multiply that number by 5/9, the fraction 5/9. If you need to go from Celsius to Fahrenheit, it is the reverse. So you take the number of degrees in Celsius, multiply it by the fraction 9/5, and then you add 32. So that's the distinction between Celsius and Fahrenheit. Another foundational distinction that we need to clarify is the difference between weather and climate. So, weather and climate are two terms that are often mistakenly used interchangeably, but they're not the same thing. Weather describes the short term state of the atmosphere in a specific location and time. It includes the conditions of the wind, the air pressure, precipitation, cloud cover, humidity, and temperature. Climate, on the other hand, describes the average long-term atmospheric conditions, including yearly and seasonal weather patterns. So, weather is the word to use if you're describing localized temporary events, and climate is the word that describes the big picture of trends and conditions on Earth. So, one example of a statement that correctly uses the term weather would be the weather yesterday was 41 degrees Celsius, whereas a correct way to use climate in context would be to say during the last ice age, the average global temperature was about 6 degrees colder than today. So now that we understand the distinction between weather and climate, we can dive into the major factors that influence the Earth's climate. And these include insolation, albedo, and the greenhouse effect. We're going to walk through these one by one, starting with insolation. So, insolation is the term that we use to describe the amount of solar radiation falling on a surface. Higher insolation means there is more sun exposure, and lower insolation means less sun exposure. And a very salient example of where we can see the effects of insolation in action is the difference in temperatures between the Earth and Mars. So if you take the average of the temperatures on all parts of Earth, it is 15 degrees Celsius, which is approximately the yearly temperature in San Francisco. And on Mars, the average temperature is 60 degrees Celsius lower than that at negative 55 degrees Celsius. And a major reason why this is the case is because of the level of insolation that each planet receives. Earth is 95 million miles from the sun, whereas Mars is 155 million miles from the sun. So, with its closer proximity to the sun, the Earth receives higher levels of insolation than Mars does. And this higher level of solar energy coming into the Earth's system is reflected in its higher temperature. But insolation doesn't just affect differences in temperature between different planets, it also affects temperatures within the Earth's system because different parts of the Earth receive different amounts of exposure to sunlight. Namely, the poles, meaning the North Pole and the South Pole, receive less sunlight than the equator does. And this is because the sunlight at the equator strikes the surface of the Earth at more of a direct up and down angle, as you can see in the illustration on the left, whereas the poles, the sunlight strikes them at more of a slant. Um, what the illustration on the right is showing is the fact that sunlight is more concentrated when it hits a surface straight up and down. So you can see that this beam of light here covers a certain distance, the one that's straight up and down. But when we take a beam of light with the same diameter and tilt it at a 30-degree angle, the surface area that the light covers is bigger and more dispersed and less concentrated. So the amount of energy hitting the surface from the angled light isn't as powerful because it's more dispersed. And this difference in the insolation at the poles versus the equator explains the very different temperatures that occur in these regions. This illustration shows the average annual temperatures in different latitudes across the globe, and you can see that the poles are obviously much, much colder than the regions closer to the equator, and this is a consequence of the different levels of insolation that the regions get. Insolation also explains why the planet has seasons and why the seasons in the northern hemisphere are the opposite of the seasons in the southern hemisphere. So when it's winter up here, it's summer down there, and vice versa. And the reason why is because when Earth is making its yearly orbit around the sun, it is also simultaneously spinning on an axis. And that spinning triggers our night and day cycles. But the axis is not perfectly straight up and down relative to the sun. It's tilted at a 23-degree angle, which causes different levels of insolation to occur in different parts of the planet over the course of the year. So here we see a representation of the Earth during the month of November, headed into the northern hemisphere winter. And you can see that because of the axis tilt, the southern hemisphere is actually more exposed to the sun during this time. So the south is leaning towards the sun while the north is leaning away. And this, of course, makes it so that the southern hemisphere gets higher levels of insolation during the winter, and the northern hemisphere gets lower levels. And down here on the surface of the Earth, this manifests in it being a hot season versus a cold season. But as the Earth continues along its path orbiting the sun, the direction of that slant changes. And at some point, both the northern and southern hemispheres are getting more or less the same amount of sun. And this is the point where it's spring and fall in one hemisphere and the other. And then the tilt of the axis starts to reverse, as you can see. The northern hemisphere is the one that is leaning towards the sun, and the southern is leading away. And as a result, the northern hemisphere gets more insolation, and the southern gets less, and this manifests in it being summer in the north and winter in the south. So the bottom line is that the tilt in the Earth's axis leads to variations in insolation levels over the year, and that's what gives us our seasons. And these images here show some differences in the level of solar insolation across the globe. So this offers a comparison between what it looks like in January versus in April. And you can see that in January, the one on the left, the highest insolation levels are in the southern hemisphere. And then by the time it's April, in the image on the right, those insolation levels are climbing higher and higher north. And finally, insolation doesn't just change over the course of the year. It has also changed over the course of Earth's geologic history in many different ways. So the solar radiation that the Earth receives has increased by about 10% for every billion years of its history. And the Earth is about 4.5 billion years old. Also, the shape of the Earth's orbit around the sun also changes over long periods of time. We're talking like tens of thousands and hundreds of thousands of years. And its axis tilt and direction that the axis is pointing also changes. So it hasn't always been a 23-degree angle that the axis is tilted at. That's just what it is right now. And in addition, the sun has a solar cycle where radiation levels peak every 11 years and then they ebb. But the impact of the solar cycle is relatively quite small. The peak levels of radiation that happen every 11 years are only about 0.1% higher than the lowest levels of radiation. But nonetheless, this is another minor factor that dictates small changes in insolation of the Earth over time.